Hey guys, Rito here with another video talking about our journey in deep learning and artificial intelligence. So today we'll be talking about transformers and LLMs. This is based on 3 Blue 1 Brown's video on transformers and how LLMs work, and specifically his deep learning 5 video in his deep learning series. So as usual, I'll have that link down in the description if you guys want to check it out. A lot of my visuals and concepts are based on his videos. So if you ever want to know the topic more in depth, just make sure to check out his videos. They are very informative. So today we're diving into something really cool: how AI understands words, finds patterns in language, and builds meaning from massive amounts of text. You might have heard the classic example of king minus man plus woman equals king equals queen. But how does AI actually learn that? So to find that out, let's break it down in a simple and intuitive way. So before we get to word embeddings, let's talk about how machines have historically represented words. The simplest way is one hot encoding. Imagine you have a dictionary with 50,000 words. You can represent each word as a giant vector filled with zeros, except for a 1 in the position corresponding to that word. Simple, right? But there's a problem. This method doesn't capture meaning. What I mean by that is something like dog and cat are just as different as dog and pineapple in this system. We need something better. So that's where word embeddings come in. Instead of arbitrary positions, embeddings map words in a high dimensional space where words with familiar meanings end up closer together. So dog and cat will be near each other while pineapple will be far away. This is because embeddings are learned from real text. AI notices which words tend to appear together and adjusts their positions accordingly. Now, here's where things get really interesting. Since words are now represented as vectors, we can do math with them. The famous example is king minus man plus woman equals queen. Why does this work? Because AI learns patterns in how words relate to each other. If king and queen have a similar relationship as man and woman, then their difference in vector space captures that relationship. So, and this doesn't just apply to gendered words. You can see the same effect with geography, professions, or even historical events. For example, if you subtract Germany from Japan and add sushi, you get bratwurst. AI is just picking up on patterns from the text it was trained on. It doesn't understand history or culture, but it can recognize the statistical relationships between words. So, how do we get these embeddings? One of the most famous techniques is word to vec. The idea is simple: train a neural network to predict words based on their surroundings. If you see the sentence, the cat sat on the blank, the model learns that mat is likely a word. After seeing millions of sentences, it builds up a sense of which words appear together, and the embeddings emerge naturally. Other methods like glove and fast text based on build on this idea as well, but the goal remains the same, which is to capture meaning in numbers. Traditional word embeddings are powerful, but they have a limitation. They assign each word to a fixed position in space, regardless of context. But what about words with multiple meanings? That's where transformers come in. These models, like the ones used in GPT, adjust word embeddings dynamically based on context. That means bank in riverbank and bank in money bank will have different meanings, different representations inside the model. This is a game changer because it allows artificial intelligence to understand language in a more nuanced way. Now that we have these word vectors, how do we measure similarity? One way is with dot product. If two vectors point in the same direction, their dot product is high. If they're perpendicular, it's 0. And if they point in opposite directions, it's negative. Another common method is cosine similarity, which looks at the angle between two vectors. This helps us quantify how closely words are related in embedding space. One thing to keep in mind with transformer models is that they process words in chunks, and we call these context windows. GPT-3, for example, has a limit of 2048 tokens. This means if a conversation goes on for too long, the model starts, quote unquote, forgetting earlier parts. Unlike humans, these models don't really have like true memory. They only see a rolling window of text. Newer architectures are improving this, but it's still a challenge for AI. So, at the end of the day, these models generate text by predicting the next word. They take their final vector representation and apply the softmax function to turn it into probabilities and choose the most likely next word. You can even adjust a setting called temperature. Low temperature makes the model more predictable, while high temperature adds more randomness. This is why increasing temperature can make AI generated text go from logical to totally bizarre. Alright, so with that stated, let's take a slightly more, or slightly less scripted approach. And let's talk about the softmax function a bit more. So let's end my slideshow, and let's take a look at this code real quick. So, showing, okay, showing this off for anyone that's interested. And let's address three questions. So, how does softmax convert an arbitrary list of numbers to a list that sums to 1? So, softmax works by exponentiating each input number and then normalizing it by dividing by the sum of all exponentiated values. This ensures that basically that all the output values are positive, since exponentiation always gives a positive number, and that the sum of the outputs is exactly 1, since in our case, each value is divided by the total sum. This is useful for probability distributions because it converts arbitrary numbers into a set of values that behave like probabilities. So let's address another question. How does softmax retain the relative order of numbers, but quote unquote stretch out the larger ones? So softmax preserves order since exponentiation is strictly increasing. It basically amplifies larger values because exponentiation grows exponentially, as the name would suggest, which makes basically the largest values dominate more significantly than their original differences suggest. So, what happens if exponentiation, or in our case, exp parentheses, is replaced by other functions? So, if we look through the code, so for us, what if exponentiation of x gets replaced by something like id of x? So, that would be the identity function. That in that a situation, it would basically normalize the values directly, but would it emphasize the differences? So I'm basically showing off why we use exponentiation in the first place and why it matters so much. Because if we were to replace this, softmax wouldn't really be the same. So what if we were to replace uh, exponentiation with something like this? So what this is doing is it's basically replacing exponentiation of x, which is the same as e to the power of x, but replacing it with 9 to the power of x, which basically it does something similar to exponentiation of x, but it does it with a larger base. In this case, 9 instead of e, which is roughly 2.718. So this faster exponential growth with this approach. It basically exaggerates the differences even more than with exponentiation of x, and it makes the highest value dominate further. So let's go a bit more in depth of what I mean by this. Since exponentiation grows faster with a larger base, differences between numbers get exaggerated even more because now we have a larger base, like I said earlier, 9 instead of e. Um, this means that the highest values become even more dominant, like I was saying, the lower values become even less significant in comparison, and the final softmax probabilities are even more polarized. So the largest probability gets closer to 1, and the others shrink closer to 0. Let's just address one final function before I end off my video here. So what if instead of exponentiation of x, we had exponentiation of negative x? So the negative exponentiation. What this would do would it would reverse the dominance. So instead of favoring the larger numbers, like exponentiation of x would normally do in its softmax function, it would favor the smaller values, and the larger values wouldn't be as favored as much. So with that said, that's it for me. Once again, check out 3 Blue 1 Brown's video. it covers the first half of this video very well on transformers and how LLMs works. He covers the softmax temperature part as well. He doesn't cover this part, but if he has a whole separate video on softmax as well. I won't have that one linked, but if you go through his channel and his series on deep learning, you'll be able to find it. I will, however, link his video that I mainly based my video on. So again, make sure to go check that out. That's it for me, and I'll see you guys later.